All right, we're going to continue to look at numeric types, and we're going to do some programs that will show some issues that we might have with numeric types and how we can change type when needed. We have to kind of remember we're going to do a lot of focus on computations because all data in a computer becomes at some point mathematical. So continuing here, we're going to look at the operations that we can do. Java has operations for addition, subtraction, multiplication, division, and the remainder operator. And the remainder operator, or modulus division, gives what is left over in integer division. So if we look at dividing 5 by 2, that will give you 2 in this first case because these were integers. And in the second case, it'll give 2.5 because Java is reading the type as a double because the decimal was put in. If we do 5 modulo 2, that yields 1, or it's the remainder. So let's actually look at this. I'm going to open my Eclipse here. Let's see if I have a good Eclipse window. Let me put a place where I can put Eclipse into the play here. Let me add Eclipse into my view. If I show all windows on this, we get a infinite screen. But let me come up here and get Eclipse. There we go. And I'm going to come over to chapter 2. I'm going to right click and I'm going to create a new class. And we're just going to call this math test. And we're going to make it public static void main, checked so that it builds the first part of the program for us. In our programs, if we do / and hit enter, it gives us a place to make comments. We should say, describe the program. For the class it's for. And the professor. And our name. And the date. Now, again, in industry, when I had come back to the programs I've written before, I would sometimes put revisions. So if I were to edit this program, I'd put a revision and the date I did the revision on it. And a reason why or what the changes were. So what we're going to do right now is we're going to print a mathematical expressions to the screen. That's all I'm doing right now. So I'm going to use system.out.println. And without the quotes, if I put a mathematical expression in, it'll print the result of the mathematical expression. So I'm going to do the 5 divided by 2. And if we run this, we notice the output is 2 because this is an integer. And if we divide 5 by 2, we get 2 with a remainder. But the remainder does not show in this mathematical operation. Now, if I were to come in and change the 2 to 2.0, Java's going to read this as a double instead of an integer. And when I run this, I get 2.5 as my output. Making sure we can see the output here. Yep. All right. So we have expressions that we can use. This can make us do, let's watch this. I'll put 5 divided by 2 is, so I'm putting the quotes in to show what the expressions, to print to the screen what I'm doing. I'll use the plus sign to tell print.line I'm adding more to it. And I'm going to do 5 divided by 2. Again, and I will put this in parentheses. Now, one of the things in our style guide is that we want to put spaces between all of our operators, with a remainder of and I'll use the modulus operator to show the remainder. So we're going to ask what 5 divided by 2 is. We'll run this, and we see that 5 divided by 2 is 2 with a remainder of 1. So integer mathematics gives us the ability to do a complete division and an exact division. This is sometimes an issue. We'll see that doubles have some issues with how they calculate. I have worked on some science issues back in the early 90s, mid-90s. Intel had a problem with their floating point operations. And in the 2000s, when I worked with some mathematical programmers, because of that problem with Intel, they had developed algorithms for working just with integers. Floating points or doubles have issues with how they represent numbers. In the core, the computer only has a finite number of values to show. It can't perfectly represent numbers because everything has to go into binary, which is finite. Where in our real number system, I can infinitely wedge numbers in between any other number. So these issues we'll want to explore, but we'll look at our operations here. Okay, another thing I want to note about operations, if I go back a slide here, is Java doesn't have a built-in for powers. If we noticed in the area of the circle program that we wrote before, we were doing radius times radius to do a power. So let's continue looking. We can talk about the remainder operation, which is what we just did. A very useful idea here of how we can do numerical calculations. If I think of 0 being Sunday, 1 being Monday, you can take an operation that calculates which day of the week it is by the remainder. Because if I divide the numerical value for counting the day and divide it by 7, the remainder will tell me which day of the week it is, because a week has 7 days. And so the remainder tells you which day of the week. And the system we tend to use is 0 for Sunday. The first day of the week is Monday, second is Tuesday, and so on. So you can use remainder operations to move through a limited list of what values. And this is how we kind of move between numerical computation and pattern lists in strings or other data types. Now, we're going to look at displaying time on a separate video here. There's a display time program in the book. But what I want to look at here first is the problem with floating point numbers. And so let me come over to Eclipse again. And I'm just going to use this program space here to do. I'm basically using my print line as a calculator right now to show what the calculations look like. And what I'm going to do is I'm going to add 0.1 Let me do this out of parentheses here. So I'm going to add 0.1 5 times. So there's 4, there's 5. So 0.1 plus 0.1. Notice again, I put spaces on either side of the operator. This is to help us visually work our way through to see in the code. And if I have to come back and edit, it makes it easy for me to get in front of the operation on a click. Well, so 0.1 plus 0.1 plus 0.1 plus 0.1 plus 0.1 should be 0.5. But when we run this, we get 0.5, which is a nice input from how the floating point worked. So we get what we expect on the package. Well, let's do this the other way. Let's subtract our way down from 1 to 0.5. So starting up from 0 to 0.5, we can add 0.01. Let's go down from 1. So 1 minus 0.1 is 0.9. 1 minus 0, or 0.9 minus 0.1 is 0.8, 0.7, 0.6, 0.5. And when I run this, I get this extra information. And this has to do with how binary is not base 10. In base 10, come over to my blackboard here. I've got to find some way that every time I click, it doesn't make a loud sound on your end here. We come over to a blackboard. We want to understand that our number representation is binary. So we have if I look at a collection of bits, we have 2 to the 0, 2 to the first, 2 squared. And yes, I got my pen fixed. 2 to the 5th, 2 to the 6th. And so here we have 8 bits numerically. And so we can only represent numbers in powers of 2. And so if we think of our base system of when we write a number like 0.1, this is equivalent to 1 times 10 to the negative first, or 1 over 10. If I were to write 0.2, it's equal to 2 times 10 to the negative first, or 2 over 10. And so there's a fractional representation that comes from our notation. 0.01 is equal to 1 times 10 to the negative second, because it's in the second place after the decimal place, which is the same as 1 over 10 squared, or 1 over 100. And so in our way of writing, fractions of base 10 work out naturally. So 1 over 10 has meaning in the decimal system. But if we write something like 1 over 3, this gives us a repeating decimal. In binary, floating point numbers have to be base 2. And so we're looking at fractions of 1 over 2 to the 0, 1 over 2 to the first, and so on, when we need to work at the decimal point. This gives us a problem that representing certain decimals, like 1/10, because the denominator is 2 times 5, 1 over 2 times 1 over 5, 1 over 5 in binary gives a repeating fraction. And what we end up with is we get what's called machine error. In trying to take these exact representations in our base 10 system, we can come up with representations that can't fit in a bit system. And this poses problems on how we do mathematics. And I'm oversimplifying. The chips have good algorithms to deal with this, but as you can see, just subtracting 0.1 from 1, we get an answer where the rounding that is done by the computer to take care of this translation from base 10 into binary causes what's going to be called machine error. Later on, when we have to compare numbers, let me go back to the screen here. I'll write this out. If we have to make a comparison between two numbers, with integers, I can ask, does my variable equal 3? And because integers move nice and neat in steps of 1, which binary can do by shifting the bits, and we don't have to worry about decimal representation, I can say is, and if when we ask the question on a computer, it'll be a double equal sign. So we're asking, is the value in I equal to 3? But when we do it with doubles, right, if I made a variable for the subtraction I did before, and I said, does R equal 0? Again, I'm not writing full code. I'm just the idea 0.5. After I did the subtractions, the computer would answer false because it had that extra 0.1 very far off of it. And so what we end up doing is we subtract the 0.5 and we ask the question, is my double value minus the number I want it to be less than some error tolerance that I put in? And this is just what we have to do to deal with the nature of the computer being a discrete machine. For some of the people in the CS major, you will take discrete mathematics, where you'll learn some of the, it's Mat 180, where we learn some of the algorithms we can do to make dealing with discrete units more efficient, especially when translating between, in our case, doubles and integers. We also have to learn this when we switch types across. So this is what we see coming across. Also notice if we subtract 0.9, which I'll come back here, we don't get 0.1. That error still introduces itself, and we get a display that is not the same as what we expected. And so, I like testing out code. I say, whoops, I hit the wrong thing here. I went to Eclipse, so I'll come back. This is what I was talking about. System.out.print, we did these subtractions. We got this error, which is called machine error because the machine is not precise in floating points. And if we do 1 minus 0.9, we'll see this result. So let's do that calculation here. And so if I subtract 1 minus 0.9 and I run it, we see that we don't get 0.1. We get something near 0.1. And so when we're dealing with doubles and we do comparisons or we do any mathematics, we have to realize these imprecisions affect the calculations, especially if we do a lot of calculations, which is what the modern world is doing with computers. Big data does a lot of computations, and we have to be aware of how the machine error can creep into our calculations. Now, we can use exponents. Java does not have a built-in for exponents, but it has the math.pow function. And we're going to do these examples, but I want to kind of talk about what math.pow does. It's coming back here. So in mathematics, we can have some number to a power. In Java, we would have to use the math library and the method inside of it called pow. And it's going to ask for the base and then the power. Now, if we when we go into Eclipse, we'll have Eclipse show us what this takes. Math.pow wants this to be a double and this to be a double. So it'll read it as doubles, and it outputs a double. But we need to notice some things we can do with powers. If I do let me do 4 to the 1/2 power. In mathematics, that's the same as saying the square root of 4. And so in math.pow, we can take 4 and use a half in its double form to take a square root. In fact, let me just say any base to a 1 over b power is the same as the bth root. So if I wanted a cube root, I would take 8 to the 1/3 for a cube root. It's the same as saying 8 cubed. Well, here we run into a problem with our double representation, because we get a repeating decimal. So we can look at the algorithms for doing powers, knowing mathematically that we have a relationship between powers and roots. And we can put that in math.pow. And we'll look at cube roots more because we're going to have some issues with the precision of decimal representations. Another thing that happens is if I take a negative root, if I go a to the a negative power, that's the same as making 1 over a to the b. And so math.pow of a to negative b will return decimal. So let's play with each of these different forms. We'll look at square roots, we'll look at powers, and we'll look at negative powers. And we're just going to play with this in Eclipse. And again, when you're programming and you're learning a new command, setting up a quick display, sometimes to view that command, can help. So I'm going to come over here, and I'm going to look at some examples of math.pow. So I'm going to do math.pow. Now notice Eclipse gives me a suggestion here, and it tells me it wants a double, comma a double. So it's taking 2 arguments into the method, and it returns back a double. And then Eclipse is giving me an idea of what the results are. And you can also notice that there's this thing called NaN for not a number. This happens when our mathematical results get us near infinity. And it has some functions built in to see when that might happen. So let's take 2, let's take 2 and let's square it. So 2 to the power of 2. When I run this, I get 4 as a double. So I can keep doing my powers of 2. I can get 4 or 2 to the cubed, which is 8. So a program we could write in our next chapters when we start learning how to iterate is we can make a table of powers of 2 to help with our binary. So let me put a system.out here. And this is 2. And in other computer languages, like Excel's, line set, Python, C, there are different ways of showing a power. Some do star to say a power. Others do the caret. I'm going to use the caret just to show what our results are. So 2 squared, or 2 cubed, is math.pow 2, 3. And so 2 cubed is this. In fact, let me change my code a bit here. I'll use print so it doesn't start a new line, and we'll put this all on one line. So 2 to the 3rd power is 8. Let's do a couple more. Said we wanted to look at fractional. So the square root of 8. Yes, and I'll use the square root function like this. I'll use a right square root like this so we can see it on the screen since I don't have a symbol for the square root. And so that is math.pow. I'm taking 8 and I'm making it to the half power, or 0.5. And I run this, and that's a decimal, or a double representation. Let's play with this. If we want to play, and this is taking doubles, let's see what happens if I give it 1 divided by 2. I get 1. So what happened here? Well, let's see here. I'm doing a division, but I'm doing an integer division. And this is where we have to watch type. So 1 divided by 2 in integer division is 0. And so this is showing me the square root of 8. It isn't showing me the square root of 8. It's showing me 8 to the 0th power. And anything to the 0th power is 1. So we have to be careful when Java is asking us for a double, but our calculation only uses integers. So if I wanted to fix this, I could do this. And now that's the same as doing a half because I forced it to give a double result. This means I could try to find a cube root. So cube root of 8 is and so I'm going to do math.pow 8, and then I'm going to note my type. So I'm going to do 1.0 divided by 3.0. And hopefully we get 2. So just be aware type matters, and the type that the methods are asking gets shown in Java. And if I made the mistake I made earlier of doing 1 divided by 2 without casting it as a double by writing a double in here, then in Java is going to do 1 divided by 2 and give us 0 back out. And that's not the question I asked. Let's look at negative exponents then. So let's do 10 to the power of negative 1. So, oops, I want to do a print line here. So again, I'm doing math.pow. I'm doing 10. And then I'm going to take it to a negative 1 power. And if I put my spaces in properly, I get the decimal 0.1 as a representation to it. So we can look at what 10 to the negative 5th is. And notice Java is going to return this in engineering notation. And it says 1.0 times e is times 10 to the negative 5th. So it translates it into a scientific notation for us. Scientific notation has 2 parts. The first part is called the mantissa. And the second part, the power, determines how many decimal places or how many zeros are in it. So this is 1.0 times 10 to the negative 5th. And we're going to explore how to get our display to show things as we want in the kind of next sub-lecture coming across. All right, so we can see our calculations and we can see some things that we have to be careful with with type, because Java is going to make some assumptions. And let's look at the assumptions. A literal is a constant value that we type in. And if we type in 34, Java is going to read this as an integer. If we type in 1,000,000, Java is going to read this as an integer. It will work, the compiler will work a little intelligently trying to use the best type for the number that we used. So putting a decimal in or putting a value that can translate to a double, Java will use a double. So integers have a size. So byte can only be, if we go back, let me go back to the chart here. Byte can only be from -128 to 127. So I'm going to come over to my code here, and we're going to set up some variables. Again, I'm just using this as a test space. So I'm going to come into my code. I'm going to get rid of what I printed out before, and I'm going to go integer or byte equals 210. Notice Eclipse. If I weren't in Eclipse, I could get a compile error, but Eclipse here is saying multiple markers at this line, syntax error, can't complete the expression. What's happening is Java, byte I equals 210. There we go. If I come back here, thought I typed the I, it's going to say a type mismatch, right? Java can't convert an integer into a byte. It'll try to convert for me, and 210 can't fit within a byte. And so I get a warning. I could try to run it, and I would get a syntax error. But if I come down in value, 126, then I just get that I can't use this. And so let's look at what happens if I have a byte, which can only go up to 127 characters. So I'm going to go system.out.println. I'm just going to print I, what's in my byte character. And so I get the 126. Then I'm going to add 1. So this is a post increment operator. If I do I++, I'm going to increase the value of I by 1. And so I'll print what happens when I do that. So I'm counting. Now I'm going to increase it once more. So I've gone past what a byte can store. And so if I run this, look what happens. It has scrolled over to a negative number. And I have filled, binary addition has filled the sign bit. And so this is called a signed bound error. And so by adding 1 past the value of what byte can store, it scrolls into negative because it fills the sign bit with a 1. And so if I were to continue to add to it, I'm now on the wrong side of the number that I wanted to be. I've moved over to negative numbers. And so we have to watch this when we're programming, that the numbers we use, we can scroll past. There's a population program in Chapter 1 that's repeated in Chapter 2 and Chapter 3. And sometimes students will use integers for counting the population, and they're stuck at 2 billion. And if you do a large projection of a population, we can go past 2 billion. And they start getting negative numbers, and it's because they went past the integer system that they had. And this is just to be aware that when doing mathematics where you increment on a number, you might sometimes need to check for your upper bound of the variable type you have. If I come back and I switch this to integer, which has a larger bounding system, I'm fine. So type is important in the amount of memory it uses. And in some programs, with large data sets, you want to use the smallest amount of memory, so use the smallest amount of type that fits the values you need to work with. Occasionally, that comes with having to make periodic checks to make sure that you're not going out of bounds. And doubles and floats have some similar issues. Now, you can always force a type by using the capital letter L to force an integer to be treated as a long. And in floating points, we can use an F to force it to be a floating point, or a D to be a double. And let's look at the difference between a floating point and a double. So I'm going to come back to Java here. I'm going to come back to Eclipse here. There we go. And again, I'm just using my Eclipse right now as a practice space to look at certain things. And I'm going to compare some divisions of the same numbers. So system.out.println. And I'm going to do 1 divided by 3. Now that's a third. But if we look at the type I did here, my type literal, this is an integer and this is an integer. So this is going to do integer division. So I do system.out.println 1.0 divided by 3.0. Java's going to read this as a double. And I'm going to get a double division, so I should get like 0.3333 with a repeating decimal that times out somewhere. But let's say I didn't want to do a double. I want to force it to be a floating point. So 1.0 floating point divided by 3.0 floating point. And let's compare the different results. So I'm going to get integer division on 1 divided by 3. I'm going to get double division on 1.0. And then I'm going to get floating point division. So different interpretations of the same numbers based on the variable type or the memory that Java is using, how many bits it's using to represent the number. And so 1 divided by 3 as integer division is 0, because 3 goes into 1 0 times with a remainder of 1. 1.0 divided by 3.0 is 0.33 repeating in our floating point operations. And we have about 16 digits. And then 1.0 floating point divided by 3.0 as a floating point has less digits and a little bit of a rounding error in it. So this is why type becomes important. On Milky Way at Home, when we first began programming on GPUs to do the calculations for us, the GPU vector units only had floating point arithmetic. They did not have the memory space or the architecture in the GPUs to deal with doubles. And our calculations weren't actually being accurate enough to use. When they added double calculations, we could start doing the calculations we needed for the likelihood methods, because we now had enough decimal places that we could separate out meaning. But we had to restrict people on older graphics cards because it would try to run and the calculations would be all off. Knowing what you need from your data and your numbers are going to be important. Now, a lot of the work we do, we can use int and double, and we won't run into any issues. But you might see some bugs in your code if you get past a boundary of the number you have. If you add past the boundary of the number, it'll scroll over to negative values. And if you mismatch types or convert to a type that isn't smooth. Another thing we can look at, scientific notation. I can enter a number into Java Eclipse as scientific notation. So 1.23456 e to the 2, or e2, is 1.23456 times 10 to the second. And so that would be moving the decimal place over. That's 123.456. And so this is some of the mathematical representations we have. I'm going to post this video up, and I'll continue with making some videos on chapter 2. I'm going to finish the lecture notes. So part 1 and 2 will be lecture notes, and then I'm going to go through some sample programs from the chapter.